lecture. I think yeah, 30 second maybe. So in this lecture, we have. So I hope the previous unit commitment thing and everything is fine. If you have any queries, you can ask me now. So okay, so let us go ahead. If no queries. So we have in the last lecture we have discussed the basic background and setup of a control problem. What exactly we are trying to control in power system, and what how to control that. That's all is going to come in this lecture as well as in the coming up lectures. But you got the idea. Basic elements what we want to control is frequency and voltage. And why do we want to do this? Because obviously these two elements affects the performance of the appliances, any devices or any machine. It hugely or it extensively impact their performance, even with their change by 1%. So 1% change is also really huge for any devices. So you can easily observe from your, I don't know if you have done your lab experiments in your bachelor courses on machines. So you must have observed that gradually, as you increase the load, the voltage changes, and as soon as the voltage changes, the frequency changes. And yeah, every element. And you have, I don't know if you have done that experiment or not. There's a light bulb type of thing, load we create by light bulbs, and those light bulbs intensity gets affected. So yeah, basically there are a lot of impacts which these two elements create, and we have to control these elements in real time. So basically, or to just to simply tell you that whatever we have studied previously, the economic dispatch, unit commitment, ACOPF, DCOPF, SCOPF, in all those things we assumed load to be constant, and then we try to solve all the problems and try to get the economical status. But now even we are assuming that loads are also changing, and the time duration is at the level of seconds and minutes. So the time is so small that you cannot think about economics at this moment. So we have to focus on the controlling and maintaining the system at a specified level or at a nominal value. And once we ensure that the system is remaining at that nominal value, then only we can go for economics. So at this small time duration, what we are talking about. So here in this diagram, you're going to see three broad loops. One loop is this AVR loop, another is ALFC loops, and in this, under this ALFC, there are two broad loops. One is primary loop and the secondary loop. So here, as we discussed in the class, this recording I'm doing afterwards because we missed a lot of recording during, there was some issue with the PPT. So you can see here that there are three transmission lines, three phase of transmission line, and this is connected through generator via transformer, and then this generator is connected with the excitation systems, and through turbine it is connected to the speed governor and the rest parts. So here just focus on the right hand side. The right hand side is for the AVR loop, which is automatic voltage regulator, and this, just by the name you can guess, the voltage regulator means it focuses on minimizing the voltage error. So obviously, as you have seen in the load flow studies, you, for every generator you give a P setting and a V setting. Now this V setting a generator has to always ensure. So this complete diagram is focusing for just one generator, right? So for this generator, whatever is the V setting, you are giving here this Vref, and whatever is the actual voltage on the transmission lines, that voltage is sensed by a potential transformer. It is being rectified and filtered and transferred to the given to the comparator. This comparator compares the set point voltage and the voltage coming from the transmission lines, and it gives a voltage error. This error is amplified and given to the exciter, where this exciter increases the field current in the field circuit and eventually increases the voltage at the generator terminal, and obviously it is transformed through a transformer, and then it again injects voltage at to the transmission line. So this AVR loop is a faster loop. It's a very fast loop. It quickly reacts, and it continuously keeps on checking the voltage on the transmission lines, and it continuously keeps on changing the field current to ensure that the voltage remains at the voltage set point. So this is a very fast loop. Now this is one part. So the right hand side of the generator, what you're seeing, this is all for the voltage. Now the left hand side, from here, the left hand side is focusing on the frequency. So as we discussed previously, the another factor which we want to maintain is frequency. Now you know that all the generators, most of the generators are synchronous generators, and these synchronous generators is dependent on the speed of the synchronous generator is dependent on the frequency. So you know that Ns is equal to 120 F by P, where P is the number of poles, which is obviously fixed. Once the generator is installed, it is fixed. So that means you can say that Ns is directly proportional to frequency. Now, as soon as any load change happens on the transmission line, immediately the speed of the generator changes. And as soon as the speed of the generator changes, the speed of the turbine, which is actually coupled through to the rotor, obviously if the rotor speed changes, then the turbine speed also changes. And this speed change is sensed by a speed sensor, and this speed sensor gives the signal back to the speed governor. Now here in speed governor, we also give, in power system, we give every generator a PREF. PREF is given. So that PREF and whatever speed you are getting from the turbine, that speed is there. You compare both the speeds and the power set points, then you get a power difference, and this power difference is amplified and given back to the some control valves are there, which will be opened or closed based on the change in the speed, and then this control valve will open and more steam or hydro, whatever is the source of energy for this generator, that is given to the turbine. And if it needs to increase the speed, it will increase the speed, means it will open the valve. If it has to reduce the speed, then it will close the valve or open the valve in a very slightly. So this step is actually known as primary ALFC loops. Primary ALFC means primary automatic load frequency control loop. So this is the second fastest loop. So obviously the first fastest, I told you, it is AVR loop. This ALFC loop is the second fastest loop. It actually reacts in the second fastest. So AVR loop generally works in every second. In every second it is continuously moving. ALFC loop actually works in few seconds to few minutes, this primary ALFC loop. And then even then, if let's say frequency does not settle down, then there will be secondary ALFC loop which will get activated. This takes roughly few minutes to few tens of minutes, not more than that. Now, how does this secondary LFC loop works? This actually, here we are only seeing that there is only one generator, right? But obviously in a practical system, there will not be just one generator, there will be a lot of generators in the network. So basically, for secondary LFC loop, the input comes from the frequency sensor, the actual frequency on flowing on the transmission line. The frequency of voltage or current, whatever, both is going to be same. There will be just a phase difference, but the both frequency is going to be same. So it sends the frequency, sends the signal to the signal mixer, where you are getting the frequency from all the tie lines. So basically whatever is the tie lines, or you can, in simple sense, you can say other generators, for all the generators, what all frequency they are sensing, that signal is being sent to the signal mixer, and here we get area control error. So this error is kind of error of frequency corresponding to all the generators and all the tie lines, and this error is integrated and changed given to the speed changer, which will actually change the P set point of the generator. And again, as soon as you change the P set point, then again primary LFC loop will come, and then it will try to set the frequency back to the normal value. So here, the idea here is basically, if I just talk about on the left hand side, so let's say if I draw this diagram in y-axis, let's say it is frequency, x-axis it is time, and at this point let's say frequency is 50 Hertz. Now, as soon as some load changes, let's say load has increased, frequency starts dropping, and it will settle down to a value decided by the ALFC loop. So ALFC loop tries to stop the reduction in the frequency, and it will settle down the frequency to a particular value. Now after that, the secondary ALFC loop gets activated, and it will try to bring the frequency back to 50 Hertz. So primary ALFC loop focuses on settling or stabilizing the frequency, and secondary ALFC loop focuses on bringing the frequency back to 50 Hertz. And here I mentioned that frequency is not exactly 50 Hertz. This is because obviously there are a lot of generators which are interacting, so there will be small oscillations, and they can actually reach at 50 Hertz, but there will be small oscillations which will continuously keep on happening, and that's why it will not remain exactly at 50 Hertz. Also, after this, once the frequency is stabilized, the third step is actually the tertiary control. So here in the first and the second step, when we are trying to stabilize the frequency, here we are not focusing on the economics. Here we are just focusing on to bring the frequency back to the normal. And once the frequency is back to normal, then at the third stage, which is called as tertiary loop, here we focuses on economic dispatch, DCOPF, ACOPF, whatever we have studied before this course, everything comes in the tertiary loop. Right, so this is the complete diagram or the plan of action what we are going to study in coming up lectures, and we'll see every component in detail. Okay, let us try to visualize this diagram. This diagram, I'm explaining the primary load frequency control, what I have just now told you before. Now here in this primary load frequency control, you saw that the initial signal comes from delta Pref. This goes to a speed governor, which actually gives a signal to a comparator, and then to a hydraulic amplifier, and then to control valve. Now here in control valve, if we want to open the control valve, that means this piston has to move down so that more steam or hydro, whatever is the source of energy, will pass to turbine, and if more energy is passing to the turbine, that means the turbine will run at a higher speed, and if we close the valve, then the less volume of steam or water will go to turbine, that means it will reduce the speed of the turbine. Now how to open and close this valve? Now let us see this hydraulic amplifier. Here this piston, which is connected with control valve, is located or is placed inside a high pressure oil tank, and this high pressure oil tank is connected through another piston, pilot valve you can say. This pilot valve, if you move this pilot valve up, what will happen here is that high pressure oil will enter from here, and here some margin will be there. It will move and it will push the piston down, and the remaining oil will go away from here. The same thing you can visualize for the reverse, that you have to push the pilot valve below, so that now the high pressure oil will enter from here and it will push the piston up, that will close the valve, and then remaining oil will go away. So this is the way you open and close the control valve and control the main piston. Now let us visualize the speed governor, which is actually connected to a flat surface here. And now you can see that this speed governor is connected to two balls are there. These are the two balls, and these two balls are connected with a spring. And this hinge is actually, you can see it's a rotating thing. It is actually connected to the turbine, and it measures the speed at which turbine is rotating. Now these two balls, black balls, what you're seeing, you can imagine from the let's say if you are holding a ball connected with a spring, and then you are trying to rotate the ball in circular motion, then if you are rotating at a faster speed, the circumference what this ball will make will be higher, and if you reduce the speed, then the spring will have its own elasticity and stiffness. The ball will come closer to you. Right, the same idea is here in the speed governor, that as you rotate, as the frequency has increased, that means the speed has increased, then that means this ball will move apart. These weights or the black balls are having its own weights. It will move apart and it will push this B point below. And if the frequency has reduced, that means speed has reduced, then those two balls will come closer and then it will push the B point up. Right, so this is basically compression and expansion is happening based on the speed and change in frequency. Now this P set point, delta P ref, is actually fixed. It is fixed from the previous setting, which is coming from the secondary load frequency control. We will see that later on, but let's assume this delta P ref is fixed. Now visualize another two thing is that this ABC, this is connected with a single rod, and it is a straight rod. There's no bend, nothing can be done. And then CDE is connected with a single rod. Now take your pen and you see this, that A point is fixed because the reference point of generator is fixed. Hold your pen in such a way that you are visualizing ABC, and hold a pen from A point, right? And let's imagine the load has increased, and what will happen if the load is increasing? The frequency will reduce. Frequency will reduce, that means speed will reduce. Now the speed governor, if you'll see, both the balls will come closer to each other, and eventually it will push the B point up, right? So it will move the B point up. So in the pen, when you're holding the pen from the A point, push the B point up, you will see that C point is going up, right? Now if C point is going up, now from CDE, now again hold a pen where E point is fixed. This valve is fixed, E point is fixed. Now you are holding and pushing the C point up. When you open, because valve and piston will always remain fixed, it will not change right now. It will change, but not now. It will initially remain fixed. And you are pushing the C point up, and as soon as you're pushing C point up, you will see that the D point is also moving up. And as soon as the D point is moving up, you see that the oil will start entering and it will start pushing the piston down. The E point will start going down. Right, now as soon as E point start going down, then you can see that the turbine or the valve starts opening. That means more steam or more water is flowing into the turbine. That means the speed of the turbine will start increasing. And as soon as the speed of the turbine starts increasing, what will happen? The speed governor, the B point, it will start, these two weights or these two balls will start expanding. And as soon as it starts expanding, the B point will gradually come down. Again, hold the pen in ABC from the A point, and you'll see that B point will start coming down. And as soon as B point starts coming down, the C point also starts coming down. And as soon as the C point starts coming down, the D point will actually also start coming down, and it will eventually close the openings which was allowing this high pressure oil to move, and the valve or the main piston will actually stop moving up and down at a particular point wherever this opening was set. And you can see that because there is a high pressure oil which is present at the top of the piston and the bottom of the piston, therefore piston will remain at stable and stand still. At that point it will not rotate. So this is the way we actually control the generators in primary load frequency control. And obviously you can change the delta pref, the set points, and you can visualize the same things. And as soon as you change the same thing, the generators starts behaving in the same way. So I hope you got the idea how it operates. So this is the primary load frequency control, and we'll see this speed governor, which is the most important part, in detail, and then we will go for secondary load frequency control, and then we'll go to excitation system. So this is the complete plan for these lectures, the coming up lectures. If you have any queries, please let me know in tomorrow's class or in the next class.